Welcome to the survey of the elementary principles in classical mechanics. Today we are going to discuss D'Alembert's principle and Lagrange's equations. Our goal is to come up with a formulation of mechanics where the forces of constraint vanish from the dynamics of the system. To this end, we define virtual displacements as changes in the configuration of a system as the result of any arbitrary infinitesimal change of the coordinates, which we will denote with delta Ri, that is consistent with the forces of constraint imposed on the system at a given time t. In a real displacement taking place during a time interval dt, the conditions, as in the forces or the constraints, may change. If the system is in equilibrium, then the total force acting on any particle is zero, regardless of what particle we choose, and as such, the dot product between the force and the virtual displacement is zero. If we sum this condition over all the particles in the system, we obtain a sort of equilibrium condition for the system during virtual displacement. And if we further decompose the force into the applied component and the component arising from constraints, we can write this equilibrium condition as a sum of two terms. We impose that the net virtual work of the forces of constraint is zero. This is always true for rigid bodies and particles fixed on surfaces, but for the latter not if dissipation is present. Excluding friction is not problematic, given that it is a macroscopic phenomenon. Rolling friction is not in violation of this condition, since it acts on a point momentarily at rest, and as such no work is done in an infinitesimal displacement consistent with the rolling constraint. For particles fixed on moving surfaces, the virtual work is still zero even though the real one needn't necessarily vanish. This is due to the force of constraint being instantaneously perpendicular to the surface. From the equilibrium condition, it follows that applied forces do zero virtual work. So once again, if we impose for this term to vanish, what follows naturally is the result here, which is the principle of virtual work. Now, in general, the applied forces are not zero, and the virtual displacements of the radius vectors will be connected by constraints. Therefore, in order to solve the principle, it must be turned in a form involving the generalized coordinates qi. The above result, however, is too static, and we would desire a more dynamical formulation. The solution was originally devised by James Bernoulli and expanded on by D'Alembert. And the idea is that we start from Newton's second law written for a particle, and we simply move everything to the left-hand side. So our condition of equilibrium states that particles will be under the effects of a force equal to the actual force, which is the one here, plus a reversed effective force, which is minus the time derivative of the linear momentum. If we now take the dot product of this expression with the virtual displacement and we sum over particles, and we split the total force into the applied component and the component arising from constraints, then we can make this vanish by demanding that forces of constraint do no virtual work, and our equilibrium condition can be written in a manner that is more dynamic in the expression here. The last result is known as D'Alembert's principle. The forces of constraint have been eliminated, but the coordinates are still implicitly dependent because of them. We search for coefficients delta qi for holonomic constraints that can be independently set to zero. So we want to express the radial vectors in terms of this set of generalized coordinates, and in that situation the velocity, which is the total time derivative of a radius vector, can be written in terms of generalized coordinates by using the chain rule for differentiation. So we end up with a sum over the generalized coordinates involving the partial derivatives of Ri with respect to Qj and multiplied with the corresponding generalized velocity plus the partial time derivative of the radius vector. As for the virtual displacement itself, when we expand it in generalized coordinates, we do not need to involve any kind of derivative with respect to time, since the virtual displacement is assumed to take place at a fixed time. Only then is the virtual displacement perpendicular to the force of constraint if the force of constraint itself changes in time. And now we will want to express D'Alembert's principle in generalized coordinates. So for the term involving the applied force, we expand the virtual displacement in generalized coordinates, and as such the result is written in terms of a quantity denoted by capital Q, which is the generalized force, having the definition here. This quantity needn't necessarily have the dimensions of an actual force, but its product with the corresponding generalized coordinate is always going to have the dimension of work. And as an example, multiplying a torque in a given direction with the corresponding rotation angle is a differential of work. Now for the term involving the time derivative of the linear momentum, first we notice that we can express this as the mass of the particle, which is constant, times the acceleration of the radius vector, and then we can expand the virtual displacement using the generalized coordinates to obtain the expression here. If we then look at the total time derivative of the dot product between what is the linear momentum and the virtual displacement, this is of course equal with a term which is just the one obtained above, without having an explicit expansion of the virtual displacement, plus a second term involving a time derivative of the virtual displacement. This term can be easily evaluated if we recognize that we can interchange the order of the operations here, so we can move the partial derivative with respect to the generalized coordinate to the left and apply the time derivative operator on the radius vector. So what we obtain in the brackets is just the velocity v, and as such the total time derivative of a virtual displacement is simply a virtual displacement of the velocity. Then we can write our term in either of these ways is equivalent to one another. So we can write, for example, the dot product between the acceleration and the virtual displacement as the total time derivative of the quantity evaluated beforehand, from which we subtract the term that we have just calculated. And then we can expand the two virtual displacements in generalized coordinates. And we see that if we do things in this way, we can factor out the virtual displacements of the generalized coordinates to obtain the quantity in curly brackets here. Now we want to look at the partial derivative of the velocity with respect to a component of the generalized velocity, so the one corresponding to the generalized coordinate qj. And we use the fact that we can regard this as a partial derivative taken after a total time derivative of the radius vector, and as such, when we expand the velocity as this kind of derivative, and then we apply the partial derivative, uh, this term will vanish as it does not depend on generalized velocities. And for this term, we obtain a simple contraction over the sum of generalized coordinates, so we end up with the expression here. So this partial derivative of the radius vector is equal with this partial derivative of the velocity vector. As such, we can rewrite our dot product accordingly. And now, if we also perform the expansion in generalized coordinates for the virtual displacement here, we obtain this general result. So we factor out the virtual displacement of the generalized coordinate, and we take the sum of over the particles from out of the brackets, and we end up with this equality. And we see that what we have here looks like so this is a total time derivative of a quantity that looks maybe like a partial derivative of a kinetic energy, and the same over here. And when we put everything together, this is exactly how we write things out. So the first dot product involves derivatives of the kinetic energy, and the second dot product is just the generalized force. And this expression with the definition of the kinetic energy and the fact that we want the principle of virtual work to equate to zero leads us to the set of to the condition here. So it's an equation involving a sum over all generalized coordinates where we have a virtual displacements of the generalized coordinates as terms having as coefficients the derivatives here. Now, the derivative of the kinetic energy with respect to a generalized coordinate is 0 in Cartesian coordinates, and therefore this term arises from the curvature of generalized coordinates. Into reaching the result expressed here, we have made no restrictions on the forces of constraint apart from them being workless during virtual displacements. The set Qj can be made from any coordinates describing the motion of the system. However, if the constraints are holonomic, we can find a set of coordinates that are independent and containing the constraint conditions implicitly in the transformations of equation 148. Then, all the variations of the generalized coordinates are independent, and D'Alembert's principle is satisfied only if all coefficients vanish separately. So in the case of holonomic constraints, we can equate all these coefficients to zero independently, and we obtain the general form of the Lagrange equations, which is written here. A first step that we can do now is to consider that the applied forces are derived from scalar potentials, and as such we can easily show that the generalized force is simply equal to minus the partial derivative with respect to Qj from the potential, and then we can work the equation here into a more compact form, which involves the kinetic energy and the difference between kinetic and potential energy. If the potential does not depend explicitly on time, the previous result describes the dynamics of a conservative system. However, the equations still hold otherwise. Since v is independent of generalized velocities, and when defining the Lagrangian L as the difference between kinetic and potential energy, then follow Lagrange's equations in their classic form. So the partial derivative of L with respect to the generalized velocity and then taken as a total time derivative must be equal to the partial derivative of L with respect to a generalized coordinate. We are now going to study a few properties of the Lagrange equations. First of all, we want to look at a case where the order in which we take the derivatives does actually matter, and it implies the kinetic energy of the system. If we take the total time derivative of this partial derivative with respect to a generalized velocity, then things just follow naturally by the chain rule, and this is equation 1. But if we now take, first of all, the total derivative with respect to time of the kinetic energy, things follow simply as written out here. But now if we take the derivative, the partial derivative with respect to a generalized velocity after this operation, because of the factor here, we end up with an extra term in the expression. And you see that if we subtract 2 from 1, these terms vanish, these terms vanish, and these terms vanish, but this one survives. So their difference is equal to this thing. And if we put it in the previous result in equation 153, we end up with what is known as the Nielsen form of Lagrange's equations. Consider now that we have something that I will call a gauge function, so a function capital F, dependent on the generalized coordinates and time, that is arbitrary and differentiable, and assume that a new Lagrangian L prime is equal to the old Lagrangian plus the total time derivative of this gauge function. The time derivative itself is simply written as here, expanded in generalized coordinates and the partial derivative with respect to time. So if we take the partial derivative of L prime with respect to a generalized velocity, the Lagrangian contributes with this term. The gauge function will only contribute with one term coming from a contraction on this sum, since it does not depend explicitly on generalized velocities. And then if we take the total time derivative of this expression, this leads to here, and this term is expanded into what you see here. If we then take minus the partial derivative of L prime with respect to a generalized coordinate, we obtain from here this term, and from this term once again a usual expansion. And now you see that if we add the two together, these terms vanish, and these terms vanish, and we are left with only these two. So you see that we obtain the same equations of motion. In other words, while the result 156 always holds for a conservative system, it is not the only way to construct a suitable Lagrangian. And in fact, we have an infinity of ways in which we can construct Lagrangians that preserve the equations of motion for a given system. Furthermore, if we have a set of generalized coordinates q, then by a point transformation to a new set of coordinates, we arrive by the following definition. So taking the coordinates q as being dependent on the variables s. Then the generalized velocity in q coordinates is expanded as follows in the s coordinates. And then the partial derivative of L with respect to a generalized velocity in the s coordinates follows through the dependence of L on the generalized velocities, and we can see that when applying this into the definition here, we get a contraction. So all that is left is a factor of this form. And if we now take the total time derivative of the expression here, we will have a term involving the derivative and this factor, and a second term involving the action of the operator on the derivative here. And of course that in this situation I can interchange the derivation with respect to s with respect to time, or the other way around. At the same time, I can take a derivative of L with respect to Sj, and the result follows simply. So if we look at these two, we notice that for the term here and the one here, this derivative factors out, and what is left is the original Lagrange equation for each particle, so for each coordinate. So these two will vanish, and the same thing happens here, given that we can interchange the order of the operations. So we can take the derivative with respect to the coordinate Sj out of the generalized velocity. It means that these two terms vanish as well. So when adding these equations together, only the left hand survives, and we have arrived at the same Lagrange equations expressed in new coordinates. So the Lagrange equations are invariant to point transformations. In summary, we have defined virtual displacements as a motion of the system at a fixed time in such a way that the constraints are workless. We have expressed D'Alembert's principle for virtual displacements as a condition of dynamical equilibrium involving only the applied forces and the time derivative of the momentum. For holonomic constraints, we have shown that the principle leads to Lagrange's equations describing the dynamics of the system. We have studied the invariance and transformation properties of these equations and the system's Lagrangian. In the following, we will discuss velocity-dependent potentials and the dissipation function. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.